Good morning, everyone. So today I'm going to present one piece of work that we are doing in NUS, like with Prof. Terence. So our ultimate aim is to create a visual learning paradigm with brain learning principles. So we are only focused on computer vision problems. So for the moment, we have found not found we read through the literature and we found and finalized few principles. So the visual learning is continuous. So actually there's no training or testing phase. So we have to learn continuously. So we have to deal with the labeled one and the unlabeled one. So how we are going to deal with that. And it favors the recent information. Suppose you read something like yesterday. Suppose you read something like 3 years back. So there's a difference between the recency. There's a temporal factor. And it uses both top-down and bottom-up processing. So in the case of deep learning, we are just going from pixels to a decision. So it's technically bottom-up. But actually, there are top-down guides as well in the actual brain. And it prefers high-level semantics. So I can show you one. Yeah, the final slide, the one before. Okay.
You mean this one?
Okay, so you can see these pictures. The first one is like an illusion. So there's a young lady as well as an old lady. So at one time you can see only once. Either you can see the old lady or the young lady. So if you take these two figures, we are giving equal semantic preference for these two images. But if you look at the second diagram, it's kind of some scratches, but if you look closely, you can see a dog in the middle. So when you see the dog, then it's difficult to unsee the dog. So in the first diagram, you have two entities.
You know what's interesting about this is every time we've showed this dog picture before, it's been flipped. So it's not the same picture that I've ever seen before. And yeah, I had no trouble recognizing it right away. It's an observation.
Yeah, but the thing is, it's difficult to unsee the dog.
I understand. I'm just pointing out there's an interesting secondary observation that
Still works.
It still
It
works.
still works? Is it really the other way
Yeah,
around?
yeah.
Wow,
I
okay.
think the picture in my book is flipped the other way.
You're correct.
Yeah.
I'm correct. It's
Yeah,
flipped.
yeah, that's
It's interesting also that I remember that.
Yeah?
I remember the shadow of the tree is up and to the left of the dog. I remember
Yeah.
that. So and
I just
that
remember
was-
the dog was facing left.
Okay.
It's interesting that's part of my memory of that image, you know.
And visual learning does pattern recognition, that's quite yes. And we usually jump to conclusions, so we don't do the whole forward propagation thing in brain. So for example, if I have a dog in my house, if it has a bell in its neck, so if I'm hearing a sound in the corridor, I'll be expecting the dog. If it's not coming, it's some unusual thing. So we usually jump to conclusions. So we take
How is it different than just pattern completion or pattern recognition?
so in
That was
pattern
the same question I asked.
So pattern recognition is I'm showing you something, you are recognizing whether it's a car or something like that.
Yeah.
This is you are jumping, you're not doing
I
any,
hear a bell and I recognize that bell is what it is.
but it's not you have to take a clear decision, right? Maybe you have to wait for some time to take the decision, right? I mean,
don't know.
in the case of a picture, you have
So I think you're making a false distinction about visual learning versus learning in general. All these attributes apply to all learning in the brain. That's my belief. That's it.
Yeah,
And
you're
I think
correct.
the jumps to conclusion, I'll just leave it at this way. I think that's an artificial distinction. I think I think it falls under pattern
Okay.
recognition. It's just an auditory sound, and you recognize it. You may have some ambiguity about it, just like you might have ambiguity about the visual image. And so I don't see.
Yeah,
that
to
as
me, they're
separate.
both sort of dealing with ambiguity.
Yeah,
in some
yeah,
ways.
and in fact, that you might be thinking it's a different sense, and you're thinking about vision, so maybe that's why you're distinguishing it, but, anyway, that was the only one that didn't make sense to me, but keep going.
So, and these are the principles yourself published in this IEEE spectrum. So I think there are overlaps, so maybe different wording. So the first one is learning by rewiring, sparse representations, and embodiment. So, and okay, so if you take a like normal machine learning problem, what we usually do is like we just put some data, just divide into training and testing. In some cases, we divide the training data into like validation and the actual training data. So we train a classifier and we evaluate on the testing data. So it's not going to work all the time. So we have to do like some learning with all these, like all the data that we have. So we are not going to get annotated data all the time. So there are lots of unlabeled data in the there are lots of unlabeled data, so we have to leverage the information from those data. So the question is how we are going to handle the delayed feedback. So I'll just explain.
What's the delayed feedback?
So I'm going to explain. Yeah.
Okay.
Yeah. Yeah. So the delayed feedback. Suppose we have a child learner. So I'm seeing the child learner like a couple of cars. So different cars. The child doesn't know about these cars, but he may know about other vehicles. So he might think like this is some vehicle, but he doesn't know it's a car. So down the timeline, maybe he will keep that in memory. Down the timeline, if somebody gives some feedback with a new car, somebody is giving something like this. So somebody is telling this is a car. So from this information, like he is able to update his learning by like labeling all these previous cars. Maybe he will keep these cars in the memory for some time. If he doesn't get any feedbacks, he will just delete from the memory. So how we are going to handle this delayed feedback? So in a neural network setting, like we tried one implementation, so I'm going to explain. Any question?
Isn't it possible? I mean, Subutai is talking about this, the nature of sparse representations, and one of the advantages you get of sparse representations is that your space of objects is naturally separated, right? They're not overlapping, and so it seems to me the way we do this is that even if no one gives me a label on anything, I actually am able to do this self-classification very, very well. I don't need a label to do that. And most of the time, not all the time, but most of the time, someone will say, that's a car. I already know what a car is. I just don't have a label for it. So it's not like I have to go back and relearn anything. It's like I already have a model for that thing, and I'm just associating the label with it. The situation comes across sometimes where you say, oh no, this is a Toyota, and here's how you can tell a Toyota, and I didn't know that before. So, but then there's some feature I look for, like the little Toyota.
Actually,
so this question is about, is it really a delayed feedback problem, or is it, because I don't think of it that way. It's not like, if you think about machine learning and neural networks, you say, oh yeah, I need this training signal to train the network, but with an embodied, sparse sensory motor system, I don't believe you need that. You've learned, you've classified the world already, and you can put a label on it or not.
It doesn't need to be a label. It can be some auxiliary information. So.
But I guess the question is, it's not a time problem, like I have to go back and redo something. That's what the word delayed is sort of implying that, right?
Okay, maybe the wording might be wrong. The thing that I'm explaining is like you're learning something, you don't know what actually they are, you are keeping those things in your memory.
Yeah.
Down the timeline, you are getting some feedback about a similar object.
Yeah.
So how you are going to learn all the things that you have in your memory.
So are you doing unsupervised learning before you get the label downstream? Is that the idea?
Kind of unsupervised, yeah.
It seems like.
Yeah.
I still don't quite understand it, but it's okay.
So I'm going to explain our approach. So the first one is just an image classification problem. So we have a neural network. So when you input an image, you will get a vector of probability. So I'm just denoting by xi and yi. So you train the baseline model using some data. So the model is M. So for the evaluation data, what we are going to do is we are going to keep a bounded queue with a fixed size, and we are going to store all these inputs and outputs as pairs in the bounded queue. So you put an image and you get the probability vector. We are going to store these x and yi pair in the queue. So actually we are going to keep like a bounded queue. So if the queue is full, we are going to do something. So I'm going to explain.
So you're saying you're keeping all this label data around, is that what that means?
These are not, we don't know the label for these exercises. So
Oh,
these
okay.
are the results produced by the network.
Okay. The probability of what? Of
Classes.
classes?
For each class.
Yeah.
But then that would be a label, right?
It's a predicted label.
Uh,
It's not a, it's a label. is
It's
ground
not the
truth.
actual label.
I
so-
see, okay. Thank you.
So this is a model, you just pass X and you get a probability vector. So we are going to store in a bounded queue. If the queue is full, we are going to update the model even without the actual label. If the queue is not full, like we are going to get the next X and we are going to update the bounded queue. So if the queue is full, how we are going to update the model? So, okay, so for this one, you can remember the example I saw. So we are going to give a feedback in the form of Z0 and Y0. Y0 is a label, so we are going to say what is this object, and we are going to pass some auxiliary information. Like you can pass whatever. In this case, we are going to pass an image. So we are going to say this is a car. We are going to show some car, and you are going to check in the queue whether you have any cars. So this is the feedback that we are generating and giving. So from this Z0, so actually using some content-based image retrieval, like we can create some features. So for Z0, we can create Z0 prime, and you have a queue of images. So for all these images, you can do the same thing. So now you have all these features, so you can find the similarity between this Z0 prime and all the images in the queue.
I have a really stupid question. Context-based image retrieval sounds like pattern recognition. What is it? How do you retrieve something content-wise if you haven't recognized
Yeah,
it?
so we use the features from there. So in this case, we are using color histograms. You can use shape. You
Okay,
can.
so it's not it could be wrong, right?
It could be wrong. Yeah, it could be wrong. Yeah.
It's untrained, right?
Yeah.
You're just doing like some clustering based on some features?
Yeah, so-
CBIR step is not trained, right?
Yeah, we did not train. So we have this queue of images, right? So you can find the color histogram for these.
And then you just cluster based on those
Yeah.
features.
So
But that's sort of the goal of the whole system is to be able to cluster them properly. So isn't it? I mean,
I didn't get your question.
maybe it's, I don't know. Can someone help me out here? It seems like the goal, in the end, the goal of the system is to give an image and you cluster it correctly and say, what does this belong to? But here you're doing a very crude method of it, so it's likely to be wrong. There's no training involved yet, right?
Yeah.
I show you two pictures of cars, unless they're really similar in some basic ways, it's not going to work right.
Yeah. So actually, like we are going to use Z as well as the values produced by the model as well. We do not exactly depend on these color histogram or shape or texture. So we are going to use the values produced by the model as well. So yes. So this is something like that. So we are going to check the distance between Z0 prime and Zi prime. So these are the input space. So we transform the input space into like Z0 prime and Zi prime. And the other distance is the label space. Actually, these are two probability distributions. So we can use some maybe KL divergence or Bhattacharya distance to find the distance between the label space. And for the distance between input space, we can use, we are using color histogram. We can, since we are using a smaller images, we are using color histogram. We can go for shape, texture as well. So what we are doing is if the distance between the Y0 and Yi is close, as well as the distance between Z0 prime and Zi prime is close, we are going to update by a very small learning rate. So A is an integer which is greater than 1. So R is the original learning rate that we use to update the base model. So in the case we think the model is learning correctly, so we are not penalizing the model with a higher learning rate. And in the other case, the distance between the label space is high. In that case, maybe we are not learning it correctly. In that case, we are penalizing with the higher learning rate. So we are just multiplicating with the fact actually these A and B can be learned. So actually we use some arbitrary values like 5 or 4, but actually A and B can be learned. So for all the other two cases we did not update. So that's what we have done. I can show some preliminary results as well. Any questions?
Well, what is the distance function you use in both cases?
So for the first one, the distance between labels with we are using Bhattacharya distance. And
Using
for
what, sorry?
Bhattacharya distance.
Okay.
You can use like earth mover distance or like KL divergence. So any two, you have to measure the distance between two probability distributions. So you can go. Bhattacharya is simple.
So you have experimented like a few distance functions.
Yeah.
Okay.
That was for the labels, and then for the Zs, these are feature representations.
Yeah,
so
color
Is
histogram.
it same kind of similar, same distance measure?
No, like for color histogram, you can use either chi-square or some correlation function. So there are like 4 or 5 different ways you can.
Okay.
I think in our case, like we use chi-square distance between the features.
So we're only making an update for images that have come in with a very similar feature representation, convex history representation, and the learning rate is based on how good we did on the prediction.
So again, back to my question earlier, if I have a large difference between the Zs, then you say I'm not going to train at all then, right?
Yeah, actually we did not decide on that. Like we had to do something, but we did not decide for the moment. Actually,
Well,
like
because I was thinking like, okay, again, that could be wrong, right?
that could be wrong.
Right, no, it could be like, hey, these are both cars, but they're very, very different on the Z scale there.
Yeah, you could have a red car and a blue car, but
Yeah,
they're the
and,
same
and,
both
and
cars.
just totally different, I don't know, so there's a million ways that primitive C by R thing could go wrong. And so the question is, how does it handle that? I'm trying to understand that. So in this case, right, being the lower left quadrant and, or the lower right quadrant maybe, and so I would never be able to merge those together.
Yeah, I think in here nothing happens in that case. I think you're probably relying on that there'll be some other example Z0, that hopefully will match
Yeah.
close enough.
Actually, like even for the like auxiliary information Z0, like we don't have to put only one image. Maybe we can put a batch of images. So the Z0, like the auxiliary information that we are giving it as a feedback. So the problem will occur like if you are using a single image, and if we can use a batch of images, like somehow we can.
It just seems, I'm not saying this isn't going to work, I'm just saying, what seems to me is that you're sort of using this untrained classification system to do your training. And so it's going to get it wrong sometime.
Yeah.
The question is, will it over time fix those problems or not? And how, it's not obvious how it would. Maybe it will, I don't know.
It's not learning, right? So I have a follow-up question, Jeff, is that the reason when we created CNNs, so CNNs are automatic feature extractors, so you wouldn't have to use manual features like we used to do in computer vision in the past. So why not use like the latent representation, one of the first layers in the CNN, instead of using this the CBIR features?
Okay, so we thought actually like CNNs are learning all these like shapes and colors and everything in the front layers. Actually they are learning. We thought like this can give like some other aspect of the color. It's not actually learning everything. Actually it's learning some aspect of color, shape and everything.
But the main difference there is that it's learning, right? As opposed to the other one, it's not learning at all. So it's doomed to fail at some point, right?
Yeah.
Yes, we know that a novel object coming in with a new color will never get clustered in with the rest, right? If you all of a sudden are in a new paradigm and you just have totally new color for this object, you have an already big cluster for with lots of training samples.
Yeah.
Is it possible to merge the clusters?
Yeah, so the thing is like, we don't actually depend on color only. You can use
But it
text.
doesn't matter, whatever it is, it's an untrained classifier, so it's going to get it wrong. I mean, you can always come up with examples that it's going to be wrong.
No, actually the baseline model was trained on some label data sets. So it's not actually like we are starting
The
from.
new thing that you're coming from could be, you're assuming that the new examples are going to be somehow similar at these base levels. But history of machine learning says that's not true, I think.
Yeah.
Especially in continuous learning, right? The whole point of continuous learning is that you have distributions which are constantly shifting.
Yeah,
And
well,
the data set
that
is
makes the
changing.
problem even worse.
Yeah,
right?
yeah.
Yeah.
So the like underlying assumption is like maybe in the down the timeline we will get a correct label for the wrong
Okay.
ones.
All right.
Yeah. And so we use like we did some testing on CFA 10, so 10 classes.
Can I ask one more
Yeah,
question on
yeah,
that?
sure.
So when can you go back? So when do you do the update? So do you expect the queue to be full and then you run
Yeah.
one big update and then
Yeah.
so it's
yeah,
how
when,
frequent do you do this?
yeah, when the queue is full, we search for the best match
Okay.
and we remove it.
Okay.
If we couldn't find a best match, we just remove the oldest one in the queue.
Okay. So it's not like frequent at every iteration. You're doing like in batch. Okay.
Not like it will take some time to like fill up the queue.
Yeah.
When the queue is full, for every new sample you have to update, right?
Okay. So you use the same sample to update more than once?
No, only one. If
After you use it, you just discard it.
Yeah.
But then your queue is empty again, right?
No, like we will remove
Okay.
only one, right?
Only the ones.
Yeah.
The queue fills up once and then it's full forever.
Yeah. Yes. So you should know this one. So actually, like we evaluated on CIFAR 10. So actually, like we used a like very small CNN with like around 60,000 parameters. So the baseline accuracy was like 65. So with various queue sizes, we just evaluated the results. Actually, like it's always possible like this accuracy may go down in the wrong direction. Like, but in this case, we tested the accuracy is increasing with the queue size. So if you are not using any auxiliary information, even with that it's increasing. But if you are using some auxiliary information, the accuracy is increasing towards 76. So there's a possibility like it can. There's a possibility like this one can do mistakes, but for this data set it's in
What is without Z? Without Z is just using the Y distance?
Y only, yeah, knows that. Yeah.
So I understand, what is the test accuracy is 65%, and then, how's it different than these accuracies? I'm confused, I'm sorry.
Yeah, so actually we are using the test data set to update the weights.
No, by test accuracy, I think you mean the baseline models.
Baseline model, yeah.
Who's baseline model?
The original small network that it was trained on before he does all his queues and
Is
updates.
this this your network, or is it someone else's network?
His
Yeah,
network, yeah.
a small
Uh-huh.
CNN, yeah.
I see. So that's what you got before you did any of this updating stuff, and then you did with these queue sizes, and then you get better. And I think, is it fair today to say that today's standard on CFAR 10 is much greater than this, or is that not right? Or, I mean,
Yeah, you're right.
yeah. So we're really showing that the effect of this training methodology on this particular model.
On a small model, but
Small,
yeah, not a state-of-the-art model.
State-of-the-art models are around like 96, 97, so
Yeah.
we won't see like much difference. So we just use a like small model, like, and 65 is the like highest accuracy was achievable with like the 50,000 base samples. So actually, like we are running another set of experiments with ImageNet. So we high number of samples, but we are not using the entire image. We are using like 1% of the label samples. So, actually, and like we cannot compare with 65.82 because like we are updating for test data sets. So actually, we are learning something from test as well. So the baseline model is not learning anything from test data. So we have to do like last time he pointed out a mistake.
So why are you learning from that? Can't you just like, so you have the full training set, you get 1% of the labels and then you apply the methodology using all the remaining unlabeled images from the training set? Can't you do that?
Yeah, that was my,
Oh,
I
that was
suggested you do it,
yeah,
otherwise
yeah,
it's really hard
yeah,
to
yeah.
To compare
know what
to
to-
anything.
yeah.
Yeah. So our goal is like current neural network models, like if you take the memory size and number of parameters, number of samples, it's very high, and we're getting a higher accuracy. So maybe down the timeline we can create models with like fewer parameters, and maybe even the accuracy might be like slightly less, but we're planning to create.
So your goal is not to be highest accuracy, but really to reduce the number of parameters.
Should be closely as possible, but with maybe like a 10-fold or
Yeah.
maybe a 100-fold decrease in the number of parameters.
In some sense, that's what we're trying to do too.
Mhm.
And so in Numenta, I'm planning to do these things. So the first one is like they have published a paper in ICML, so they published this sparse network thing. So then
Who's
one
they? Us.
Us.
oh, sorry.
That was the wrong word usage. I think. You're totally stupid.
So there is one thing called CPC. So using CPC, they are producing like this is unsupervised learning. So from using CPC, they are producing embeddings which can be used to get higher accuracy classifiers. So I'm trying to use, even for this CPC, they are using neural network with like millions of parameters. Still, they depend on like large networks. So I am planning to use sparse networks to find these embeddings and compare the results. So
We had a series of talks last week about CPC.
Yeah.
So I don't know if you saw that or not. Probably should watch
No, I
it.
sent him the
Okay.
I sent him the paper.
And Stefan's
stream
coming
that.
today.
Oh, we didn't
so
stream that.
Hmm?
you
Okay.
can Stefan.
Stefan, yeah, I told
He's
him
coming
about it.
today.
Yeah,
so-
yeah, yeah.
Sure.
So I gave him the CPC papers to look at, and he's got some code.
Great.
Found some code, so we'll see.
So actually, even in CPC, they rely on like very large networks like ResNet and all this. So maybe like we can just replace ResNet with our sparse networks, and we can check whether like we can produce embeddings which can produce similar results.
So I thought CPC had this, it's all based on a temporal sequence, it's like sequence learning. So is that not right? Because you're essentially trying to predict future time steps, contrasting the next time step.
But you can adapt to image, right? Like
Yeah.
to predict
Right.
patches of the
Yeah.
image
Yeah.
around
So-
the line.
So
Top
that-
patch can try to predict the bottom
Yeah,
patch.
they're doing like when visual
they're doing
windows.
something like this. So if you have an image, yes.
So I was thinking of the CFAR10 paradigm still. So you're gonna take CFAR10 images.
Yeah, that's the problem.
Some
CFAR10 is quite small,
Right.
so we can't just divide into small segments.
So you'll use larger images.
Should be.
Yeah.
Otherwise, it's difficult to get the context.
Yeah.
You can try tiny ImageNet. I think they are 84 by 84. I think
Yeah.
it's better than ImageNet's like
Yeah.
229 by 229. That's huge.
Yeah, I have a GPU, so I have all the ImageNet data, so I can just
Oh,
run
okay.
it. So maybe during these 3 weeks, I should be able to produce some results on sparse networks. So I got the code, so I should be able to run some.
Great.
I still have a question on the queue.
Okay.
So, if I see like a blue card 3 times, okay, and I see a blue card 3 times, but I don't have the label, and the fourth one I see is a blue card as well. So Z is gonna match, right? So I'm gonna use all those 3 samples on label to learn, and then I'm gonna discard those 3 samples, and my queue is gonna be empty again, right?
Yes. So it
Okay.
depends on your queue. Like if
Okay.
you have a longer queue, like that's why the accuracy is
Uh-huh.
improving with the queue size.
Okay. But if I use all my samples, my queue is gonna be empty. It's not always gonna be full.
Yeah.
Okay. Just that I wanna make that clear.
So I think I understood the mechanics of what you said, but I didn't understand it in a deeper way. I'm trying to understand, okay, I got the idea of a queue, you're saving up these samples, you're gonna use them for training later. But I'm trying to put that into sort of a deeper understanding of how that contrasts to other approaches, and it's not obvious to me. I'm trying to sort through all these things, keep them somehow organized in my brain, and I don't know if anyone can explain that to me, like how to think about this.
Actually, like most neural network models are like quite instant. Like if you get a sample, you just update.
Yeah.
So in this case, we are keeping like queue of samples. So
Yeah.
actually, it increases the context. So like not a single sample. So like you have a
But why is that? I mean, if I'm training on every sample, then I'm using all those samples. So what you're saying is by having a queue, somehow I'm able to, by grouping training samples together, that somehow that's better than training individually.
yes.
But it's not obvious to me why.
It's because you can use past samples, because his scenario is that you don't have labels for everything. So you're in a continuous learning scenario,
Yeah.
and you see a lot of things without labels, and then sometimes you see something with a label. Then what he's saying is that when you get the label, then you can search for all other examples you have seen without the label. And then you, instead of learning just from this sample, you could just
And you're
learn.
hoping that from all those unlabeled samples that are similar, that they might be correctly.
Yeah, you're
Might be,
hoping
yeah.
that they will be the same. That's the key.
So there's
thing,
no
right?
real unsupervised learning going on here. It's just
Yeah.
it's finding a supervised label.
Yeah,
you
and
know,
then.
for past
and-
examples.
And hoping against hope that's gonna, those other ones in the queue are gonna work.
Yeah.
So that's what k-nearest neighbors is as well, right? This is sort of just like adding a KNN block to a neural network when there's no labels. You just fall back on KNN. Is that a way to look at it?
Yes, I think that's right. But and on top of that, you're also training the model then on this new imputed.
On this new
Yeah.
cluster,
Yeah.
you can do something like that.
Mm.
So KNN provides the
So
moves on that.
moves the point around a little bit.
Right.
Yeah.
Actually, I tried this idea for like unlabeled data, but I think nobody else has done it for like labeled data. So, I mean, even for the normal training, we can check like we usually update the training learning rate by like over epochs, right? Maybe we start with E-4, then like E-5, something like that, right? So actually, if we are learning something correctly, like we don't have to update model with a higher learning rate, right? So maybe like after first epoch, like you can get the results, right? We usually go like 20, 30 epochs, right, to get a good result. So
You're saying adjust the learning rate based on how
yeah,
we're doing.
so if
Isn't
you
that what backprop is?
So if you have a neural network, like you usually like have learning rate something like this. You usually have an array of like learning rate. So for the maybe for the first 10 epochs we use this, maybe for the next 10, and we never use learning rates for individual samples, right?
Yeah, but backpropagation takes the amount of error and then updates weights based on the amount. So
Yeah.
that.
Yeah, I'm telling like even with the error there's a factor of R. Right?
What's that?
That the learning.
Learning rate.
Yeah. Mhm.
So this R is fixed, right? Even whatever the error you have, this R is fixed, right? What I'm saying is like if you are predicting a label correctly, I'm saying this R should be low. If you're doing something correctly, like this
Well,
R should
but I understand what Jeremy is saying. He's saying that the gradients are going to be low. So even though the learning rate is still high, the gradients are going to be low. So if you're predicting it correctly, it's not going to change the network at all.
what I'm saying
Is
is
that what you're saying, Jeremy?
Mhm. Yeah.
Yeah.
If you get the classification exactly right, there's no update.
There is no
Just
update
like
at all.
minimizing the learning rate. So what additional benefit do we get from having a separate learning rate also?
what I'm saying, this R is kind of fixed, right? Whether it's
Yeah.
positive or negative sample, right? So what I'm saying is if we are learning something, we will update the weights, right? Even if you are learning correct. So what I'm saying is if we are learning correct, like we can update with the like smaller weight.
Actually, if you're exactly right on the classification, like if your distribution is a point distribution of 1 on the right label,
Yeah,
there should be
then
no update.
no update, yeah.
Regardless of R.
Yeah, yeah.
So-
But we don't get the exact value, right? You will get
Yeah.
something like a y vector, right?
I-
You won't get a one-hot vector in a neural network,
Yeah.
right? So you will get something like 0.8, 0.3.
So you're saying there is still like small updates and we can push
Yes,
them further
exactly, we can
down.
push, yeah.
I guess in a typical backprop, you take the difference between the predicted and the actual label, and it's some function of that. So the closer it is, just like you're saying, this is like an additional factor on that somehow. Like it's just
It would be a
changing
function
how
of
that
the same
scaling
difference
happens.
though, right?
Hmm?
The whatever you set R to is still a function of how big the difference is.
Yes.
Yeah.
Yeah. I think that should work. I didn't try, but this should work. We should be able to.
It's
push-
like it would be like in the vicinity of adaptive learning rate models like Adam. So Adam also fixed that because it's taking like the moving average of the
Moving,
gradient. So Adam's a way of fixing that. It would be like an alternative to Adam, right? That's what you're saying. Cool. So you're gonna work on that?
I didn't work.
That's just an idea.
Just try.
I think right now, while he's here, he's going to focus on sparse networks and try to get results with that.
Sounds like a good
Yeah.
idea.
Cool. Thank you.
All right,
Thank you.
thanks.
Thank you.
Thanks, Pranavan. Now I know what you're trying to do.
Were there any other research topics today? Okay.
In your book, you always tell about like without dealing with time. In all the computation vision problem, we are just dealing with images, right? In your book, I read your book on intelligence.
Yeah.
So like you always tell like without like dealing with temporal thing, we are not going to build intelligent machines, right?
Yes.
Even I have the same intuition. So like, do you have any like workarounds in that line?
Our whole sensory motor stuff is,
Yeah, we have a lot of papers on that.
yeah.
Yeah.
Everything we've published in the last few years, almost everything is related to time
Okay.
and
Okay.
movement.
Maybe.
Yeah, in fact, our work in sort of image classification is very, very recent. It's always been like this is a subset of inference. So my first comments to you as we started here, I'm thinking about how the brain builds, models, this kind of stuff Mark is talking about. Yeah, kind of stuff Mark is talking about, where the spatial inference is a sort of corner case of the general purpose sensory motor inference, and helps us understand that. But all the papers we published recently are all about, other than the ICML paper, they're all about time-based inference, everything. So.
All right, I'm gonna stop the stream. Thanks everyone for watching.
Okay.
Yeah. I like to be